Welcome viewers. In this video we will see the types of a DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. So the types of the DC generator. So based on the excitation of DC generator are classified as follows. The classification is based on the excitation given to the DC generator. Excitation means the supply given to the field winding in order to make it as a magnetic field. So in that there are two types available, separately excited or self excited. So primarily two types. The excitation is given separately to the field winding in order to make it to as a magnet flux in order to produce the flux, or self excited. These field windings are connected with the armature. So by self itself it will produce the magnet by using the concept called residual magnetism, right. So based on the excitation the generators are classified. The major classification is separately excited or self excited. Excited means giving the supply to the field winding in order to make the magnetic field, so that produce the flux. So that we have separately excited, separate DC supply is given to the field winding for excitation. Here the field winding is connected in series with the armature, so the self itself it will produce the magnetism, right. So the separately excited, self excited. The self excited again it is classified into three different type, that is the armature winding and field winding, how it is connected. So it is connected in series, mean it is a series generator, armature winding and field winding. If it is connected in parallel, means shunt generator. Both having shunt winding as well as series winding, means it is compound generator, right. The field winding is connected series here, field winding is connected in parallel here. Here both connected in series as well as parallel, so that is called a compound winding, combination of both series and parallel. This compound generator again it is classified into two different type, long shunt compound generator, short shunt compound generator. Short shunt means the shunt winding is connected immediately to the armature, thereby series winding is connected. Long shunt generator means the series winding is connected immediately to the armature, the entire circuit is connected in series with the shunt winding, shunt field. So that is called a long shunt or short shunt. The detailed diagram is available at the time, we are able to understand easily, right. So in this short shunt and long shunt we have the series field winding as well as shunt field winding. Two windings are available in both the type. So due to the two winding again it is classified into two different type, cumulative compound or differential compound. If series winding and field windings are added together, then it is called a cumulative compound. If it is opposing each other, then it is called a differential compound. That is applicable for this type also, short shunt compound generator, right. So this is the classification. We will see this classification, we will see the types one by one. So first we will see the separately excited DC generator. The generator where field winding is excited or energized by external DC source is called a separately excited DC generator. The excitation is given separately. Now we will see the diagram. So this is the armature winding, rotating part, armature winding. This is the field winding, stationary part, right. So the generator, so it will generate the power, the energy that is available in the load end. So for this field winding, it is given, the excitation given separately by the another DC source through this rheostat. In order to control the voltage applied to the field winding, this rheostat is used, right. So the DC supply is given while adjusting the rheostat. This winding become, field winding become, current will flow, then magnetic field will be created, right. So this excitation is given separately. This is the field winding, this is the armature winding, right. So due to this interaction between this armature and field winding, the EMF is generated. EMF is generated in the armature, so that is available at the load terminal, right. So this is the field winding RF, is the field current, rheostat and DC source. This RA is the armature resistor. Current flowing from the armature is the armature current IA. While going to the load end, it is IL. Right. So this EG is the EMF generated inside the armature, but while going to the load terminal, some drops will be there. So that is nothing but this the armature resistance drop IARA, and as well as load voltage, right? The EMF generated from that, this armature resistance drop is subtracted, the balance will be available at the load end, right? So these details are given here. So the IL is the load current, IA is the armature current, IF is the field current, RA armature resistance, IF RF field resistance, EG generated EMF. Now we'll see the equations. So the output power is nothing but V into IL, the load voltage and load current, V into IL. So in this case, this IA and IL both are equal. The current from the armature is equal to load current, both are equal. So by applying the KVL, the EG, this is the voltage rise, this is voltage drop. So the EG is nothing but IA minus EG minus IARA minus V equal to 0, or otherwise the generated voltage E equal to the voltage available at the load terminal plus the armature resistive drop IA into RA, right. So the generated EMF is the sum of the voltage will be dropped across IARA, the remaining available at the load terminal. So the sum of these two is nothing but generated EMF, EG equal to V plus IA RA. So there is small drop in the armature circuit, that is called IA RA. So the power developed in the armature is EG into IA, generated EMF into IA, but while going to the load end, it is V into IL. Some voltage will be dropped here, so some of the power will be reduced, the balance power available at the load end, right. So this is inside the armature, this is outside the armature, that is the load terminal. EG into IA is while going to load end, it is V into IL, right. So there is a small drop called IA and RA, right. Now we'll go to the second type. So self-excited DC generator. So previous one separately, the separately excitation given. Now it is self-excited, that is a DC generator where field windings are excited by the current supplied by the generator itself, are called as self-excited DC generator, right. The current from the field winding, the generator where the field windings are excited from the generator, the current supplied by the generator itself is called a self-excited. There is no external circuit is required. How it is possible? This is due to the property residual magnetism. What is residual magnetism? Where some flux is always present in the pole of the machine, even after the removal of the supply, some of the flux will be always available in the winding, that is called a residual magnetism. Now we will see the residual magnetism in detail. The property of the magnetic material to retain the magnetic property even after the removal of magnetizing current is called a residual magnetism, right. So after removing the supply, some of the flux will be there, some of the magnetic force is available, that is called a residual magnetism, right. In such machine, the field windings are interconnected with the armature winding, right. The field winding and armature windings are interconnected. The field coil may be either in series or in parallel, or both in series as well as parallel with the armature winding, right. So this armature and fields are connected in a three different way, either in series or parallel or both series as well as parallel, right. So that due to residual magnetism, the field windings are become the magnet, and also this armature winding field winding is connected. So the current generated from the armature is passing through the field winding also. So based on that, it is classified as shunt generator if it is connected in parallel, field winding and armature winding. Series generator, both field winding and armature windings are connected in series. This compound generator, both connected in series as well as parallel. Now we will see these types one by one. So in the shunt generator, the generator in which the field winding is connected in parallel with the armature winding. If field winding and armature windings are connected in parallel, then it is called a shunt generator. Now we will see the diagram. So this is the armature rotating part. So this is nothing but a brush. This is a field winding. Now both are connected in parallel, right? So the current generated from the armature is used to excite the field winding also. So that it is called a self excited. Now this is the load end. Armature as well as field are connected in parallel. So that called a shunt generator. Now we'll see this. So the generated EMF will be generated inside the armature. It's called EG. This RA is nothing but a armature resistance. So the EMF generated, so the sum of the value will be dropped across this armature resistor in the RE. The balance will drop across, balance will go to the voltage, the load terminal voltage, and also some of the voltage will drop across this shunt field winding also, right? Now we'll see the term. So this is the EMF generated inside the armature resistance. Then we have this IA. So here the IA will come. So that IA will be splitted, ISH and IL, load current and shunt field current. So based on that we will see the equation. The output power is nothing but V into IL, terminal voltage into load current. But what is the power generated in the armature? EG into IA. EG into IA is the power generated in the armature. After the drop, the balance will be available in the load terminal, right? So it is very, you need to clearly, we need to explain. The voltage V is the voltage available in the load terminal. EG is the voltage generated in the armature, right? So both are not equal. This EG, there is some drop will be there, balance will be available as a load terminal voltage, right? So that we will see this equation. Here IA equal to IL plus ISH. The armature current flowing from the armature is splitted into ISH and IL. So ISH, the current flowing through the shunt field winding is nothing but V divided by RSH, because the voltage across this RSH is nothing but voltage across the load terminal. Both all are connected in parallel, right? So what is the equation, the KVL? EG minus IARA minus V equal to 0. So this is the voltage rise. These two are voltage drop. Or otherwise bring these two term in the left hand side, so that right hand side, so that EG equal to V plus IARA. The EMF generated inside the armature is equal to the terminal voltage plus the drop IA into RA, right? So that these two are not equal. Sum of the voltage is dropped across the armature. Balance is available as a load terminal, right? So this is a very important equation. EG equal to V plus IA RA. Generated voltage equal to terminal voltage plus the resistive drop, armature resistance drop, IA RA. Now we will see the further detail. So IA equal to IL plus ISH. So for effective power to the load current IL should be very high. Right? If the load current IL is very high, means the power will be more. So that ISH should be very small. The current diverted through the shunt field winding should be lesser, so that IL will be more. So the ISH is made to high resistance, so that less amount of current will flow. The high resistance mean it is made up of many turns of thin wire, so many turns available, so that only less amount of current will flow through the shunt field winding. That is, the shunt field winding, the current is very less, so that the resistance were increased. So it is made up of many turns, right? So if ISH is very small, mean the IL will be more. If IL will be more, mean more power will be delivered to the load circuit. Now we'll go to the second type. Second type is the series generator. Series generator means the field winding is connected in series with the armature winding. Field winding and armature windings are connected in series. Now we'll see the diagram. So this is the armature winding, rotating part. This is a field winding, stationary part. Both are connected in series. In previous type it is connected parallel. Now it is connected in series. So what will happen here? the current flowing from the field winding, the current flowing from the armature winding, IA is equal to ISH, current flowing through the series field winding, and also it is equal to the load current. So, the only one current is available. This armature current, current flowing through the series winding, load current, all are equal. That is given here. IA equal to ISH that is equal to IL, right. So, this generated EMF is EG, right. The generated EMF will be EG. So, that some of the voltage will be dropped across armature resistance and also dropped across series field resistance. Balance will be available at the load terminal. So, that is very important. The voltage generated inside the armature EG, after the balance, after the drop across armature resistance and series field resistance, balance will be available at the load terminal, right. So, that is given here. EGIA equal to EGISC plus EG into IL. All are same because current is equal. What is the equation, voltage equation? EG minus IARA minus ISC RSC minus V equal to 0. So, this is a voltage rise, voltage generated. These are all drops. Drop across armature resistance, drop across the series field resistance, drop across the load terminal. So, it can be written as EG equal to V plus IARA plus ISC into RAC. That is EG equal to V plus IA into RA plus RAC, right, because IA equal to ISC. So, the generated voltage is equal to terminal voltage plus drop across the armature as well as the field, right. Some of the voltage will be dropped, balance will be available as the load terminal, available at the load terminal, right. So, the remaining term is the output power if you consider V into IL, the terminal voltage into load current, right. Now, we will see the further detail. Since the series winding carries full load current, the value of RSC should be less. RSC is designed with a few turns of thick wire, right. The RSC, because if the RSC is lesser, then only the full amount of current will flow, right. If the RSC is very large, means the current will lesser, but here all are connected in series. So, we need to increase the current flowing through armature as well as field winding as well as load, so that RSC should be lesser, right. So, RSC is designed as lesser, so that very few turns available with a thick wire. In previous case, it is opposite. So many turns are available with a thick wire. RSC is more, right, because it is diverted, it is connected in parallel. Now, it is connected in series. We need to increase the current, so that RSC is kept to very minimum value, so that very few turns with thick wire is available. Now, we will go to the third type. The third type is a compound generator. That is, it is a generator in which few turns of field windings are connected in series, few turns of winding is connected in parallel with the armature winding. So, both series as well as shunt, series as well as parallel is connected. The field windings are connected series as well as parallel, both are available. So, that is called a compound generator. In the first type, only shunt winding connected in parallel. In second type, only connected in series. In the third type, both connected in series as well as parallel. So, based on that, it is two type, long shunt and short shunt, right. The shunt winding is available after the series. Here, short shunt means the short winding is available immediately, after that series winding will be available. We will see the diagram, so that you are able to understand. So, due to the two winding, again it is classified into cumulative compound or and differential compound. Whether the two windings are added together means cumulative compound. Two windings are opposing each other means differential compound. Now, we will see the diagram. What is cumulative compound and differential compound? See, this is the two windings. This is a series field and shunt field. The compound generator, we have both series winding as well as shunt winding. Is connected in series as well as parallel. See the current direction, both are equal. The current enters here and leaves here. Here also current enters here, leaves here, right. So, that the magnetic pole, magnetic flux will be same in both the series winding as well as parallel winding. So, it is a cumulative, both will be added together. That is given here. If the flux produced in the series field winding and shunt field winding tends to aid or support each other, it is said to be a cumulative compound generated, right. So because of same current direction, both the flux will be added together, so that is called a cumulative compound. In case of differential compound, see the current direction, current enters in the top coil, but here current enters in the bottom coil. So the both the current directions are opposite to each other. So for example, here N pole created means here S pole will be created. So both will oppose each other. So that is called a differential compound generated. The current directions are not equal, both are opposite to each other. That is, if the flux produced in the series field winding and shunt field winding tends to oppose each other, then it is said to be a differential compound generator, right. Here current directions are opposite and flux also opposite, so that called a differential compound generator. Now we will go to the long shunt and short shunt. So long shunt compound generator means the generator in which the shunt field winding is connected in parallel across the series combination of series field winding as well as armature winding, right. The shunt winding is connected across these two windings, so that is called a long shunt. We will see the diagram, so it is easier to understand. So this armature winding is available, immediately the series winding is connected. Across these two, field winding is connected, shunt field winding is connected, so that it is a long shunt. The series winding is coming immediately, shunt winding is coming afterwards, so that is called a long shunt, right. This long shunt mean the shunt winding is connected across the combination of series winding as well as armature winding, right. Now we will see the diagram. So this is the generated EMF EG, this is the load terminal voltage. So after the drop, the balance voltage will be available at the load terminal. What are the drops available? This RA, armature resistance, armature resistive drop. Then this shunt, then series field is available and shunt field also available, right. So what about the current? Here IA, the current coming out of the armature winding is IA, while flowing through the series circuit is ISC. So both are equal, IA and ISC are equal, armature current as well as series field current are equal. So at this point it is splitted, load current and shunt field current, ISH and IL, right. So IA equal to ISC, that is equal to sum of IL plus ISH, right. So we will see the drop, what are the drops available. So the output power will be V into IL, load terminal voltage and load current, right. So the power generated inside the armature is EG into IA. After the drop, the balance will be available here. So what are the drops here? IA equal to ISC, the armature current and series field current is equal. Similarly, IA equal to IL plus ISH. IA is split into load current into ISH. So ISH can be written as V divided by RSH, because RSH is connected across the load terminal, right. So that the same voltage will be applied across RSH also. So the current through the shunt field winding is V divided by RSH, right. Now we will see the voltage equation. So EG minus IARA minus ISC RSC minus V equal to 0, right. So this is the generated EMF, that is converted into sum of the voltages dropped across armature resistance, sum of the voltage drop across series field winding, sum of the voltage drop across the load terminal, or otherwise you can write it as EG equal to V plus IARA plus IARSC, right. So the terminal voltage, the generated voltage equal to terminal voltage after this drop. The balance, after the drop, balance voltage is V, right. So it can be written as IA, because this ISC both are, this ISC is equal to IA, so that we can write IA into RA plus RSC. So the generated voltage is dropped across the load terminal after this drop across armature as well as series field resistance. Now we will go to the short shunt. Short shunt generator, see here, this is the armature rotating part. Immediately the field winding is connected, so that is called a short shunt. After that only series winding is connected, right. immediately the shunt field winding is connected, so that is called a short shunt. After this only the series field winding is connected, so that is called a short shunt, right. So what are the what are the parameters available? This Eg is the generated voltage, V is the voltage available at the load terminal. After the drop, the remaining voltage will be available at the load terminal. So this Ra is the armature resistance. This Ia is the current flowing from the armature. At this point, what will happen? Both will be splitted into ISH and ISC, shunt field current and series field current. This armature current is splitted into the shunt field current and series field current. This series field current is equal to load current also. Both are connected in series. So ISC equal to IL. Right. Now what are the drops available here? We'll see this diagram. Eg minus Ia Ra minus Isc Rsc minus V equal to 0. Right. The generated voltage, from that armature resistance drop is subtracted, series field resistance is subtracted, then load voltage, that is equal to 0, or otherwise Eg equal to V plus Ia Ra plus Isc Rsc. The generated voltage is not fully available as a load terminal. Some of the voltage will be dropped across the armature resistance, some of the voltage will drop across the series field resistance. This after this drop, remaining will be available as a load terminal, right. So the other terms are output power equal to V into IL. Power generated inside is Eg into Ia. So we already discussed Ia equal to Is plus Ish is splitted, but Isc equal to IL, right. So Ia equal to IL plus Ish. So the Ish can be calculated as Vsh divided by Rsh, right. So the remaining voltage after the drop, the remaining voltage available at the load terminal. So coming under short shunt generator. So in this video we discuss about the various types of DC generator, that is separately excited, self excited, again shunt generator, series generator, compound generator. Again it is split into short shunt, long shunt, then further classification, differential compound and cumulative compound, right. So subscribe this channel for more videos. The link is available in the description box. The material link also available in the description box. Thank you.